Okay. Thank you so much for the introduction. So as the chair mentioned, my name is Ashalatha Kunnappilly, and here I will be talking about my paper from UML modeling to UPPAAL model checking of 5G dynamic service orchestration, co-authored with my supervisors, Backeman and Cristina. Let's jump into the introduction. I would like to introduce you to the so-called 5G revolution. So in the recent years, what we have witnessed is there is a tremendous improvement in Internet of Things technology and information and communications technology that led us to development of various diverse applications. As you can see in my screen now, there are applications of different performance requirements. Some require low latency and reliable communication. For example, the autonomous car application. Some requires an enhanced mobile broadband, for instance, the robotic surgery application. And there are some applications which require massive device connectivity, like the smart home application, the smart factory application, etc. So a single network that fits all these applications of various requirements is not a feasible option. So in 5G, what we see is that so in 5G, there is a new concept called end-to-end network slicing, where the entire network is being sliced into different chunks, each capable of each capable of catering a particular requirement, be it low latency, high bandwidth, or improved connection density. So they share the same physical infrastructure, but logically they are different slices. So in a 5G network slicing, we have what is called virtual network functions that are chained in a particular order, which is defined by what is called a VNF forwarding graph. And this is what that enables an application to fulfill its requirements in a particular use case scenario. So as you can see from my slide, there are different ways a VNFs can be chained in a particular slice. For instance, it can be a simple sequence. For example, slice 2, as you can see in my slide, where VNF1 needs to execute first, after which VNF2 needs to be executed, and after which VNF3 needs to be executed for slice 2 application functionality to be satisfied. There is also the slice 1, where you can see a much complex structure where you have different options or different branching options to choose from. Say, for instance, after executing V2, you have the option of executing V3 or V4. So this is the slicing concept. And now let's go to the topic that is being highlighted in my paper, the dynamic 5G service orchestration problem. So let us imagine that we have a different 5G user equipments. In my scenario, I present two 5G user equipments. User equipment 1, which accesses a slice 1, which is a VNF chain of 3 VNFs. So in this paper, we assume only a sequence, that is VNFs are chained from in the order V1, V2, V3. And there is a user equipment 2, which accesses slice 2, which is a VNF chain of VNF 2 and 5, and they use the same overlay network where you can see 3 different hosts. In our case, the hosts are virtual machines that host these VNFs, onto which different VNFs needs to be allocated. So this is one problem, which is called the allocation problem, where you have VNFs of different requirements. Say, for instance, they have CPU requirements, they have memory requirements, they have storage requirements, and they need to be allocated on these virtual machines, which have also these resource constraints. So while doing this allocation, we need to respect that the allocation constraints are met. And as you can see, these virtual machines are connected via virtual links. H1 and H2 are connected via link L1, and H1 and H3 are connected via link L2. And these links also offer some additional constraints in terms of latency and bandwidth with respect to the traffic that can be traversed across these links. So now let us think of how UE1 can access slice 1. So for that, you have already V1 allocated in host 1. So after executing V1 in host 1, you need to execute V2 and V3, and you find that V2 and V3 are in host 2. So you need to have a routing mechanism from host 1 to host 2 where V2 and V3 is located. So as you can see from my slide, the routing for slice 1 is from host 1 to host 2 using the links L1. For UE2, which needs to execute V2 and V5 in sequence, we see that V2 is in host 2. So it executes V2 there, but and then it needs to execute V5. But we see that there is no direct connection between host 2, where V2 is hosted, and host 3, where V5 is hosted. So instead, it needs to traverse through links L1 and L2 via host 1 to reach host 3. So this incurs additional latencies and additional bandwidth constraints offered by link 1 and link 2. So this problem of allocation and routing is what we refer to in this problem as the service orchestration problem. And why it is called dynamic? Uh, as you know, there is this problem where you have a dynamic network load which is offered by different user equipments accessing this overlay network simultaneously. So when you have different user equipments being activated simultaneously, being activated periodically, and they need to share these overlay network, and also we see that they need to share some VNFs, and also they need to share the links such that the link bandwidth gets utilized only when a slice requests it, or when a slice needs to send its payload and it has to be released afterwards. So all these dynamic constraints, when imposed on this network, it will constitute what is called a dynamic 5G service orchestration problem. One example I will present in my next slide. So here is an example of two user equipments, UE1 and UE2, getting activated simultaneously. We don't show the link aspect here. We just consider the execution of the VNFs. And here I show an example where different VNFs gets executed in different hosts. So for instance, here in my previous figure, you have seen that this is the allocation, and these are the VNFs that needs to be executed in different hosts. What you see in orange are the VNFs for slice 1, and what you see in green are the VNFs for slice 2. So if you see one scheduling instance or a scheduling diagram with respect to one scheduling algorithm that executes, we can see that here is a deadline for slice 1 and here is a deadline for slice 2. But due to the scheduling algorithm, the deadline for slice 1 is missed because it schedules VNF5 before VNF3 of the slice 1 is scheduled. But if you can look at the next slide, it is more intelligent scheduling algorithm which schedules the VNF3 immediately after VNF2, knowing that the deadline for slice 2 is a little bit further, but the deadline for slice 1 needs to be met initially. Then we see that these scheduling algorithm meets the deadline. So there is this different aspect of scheduling also influences the dynamic network behavior. So this is what we will discuss more in this paper. And as you can see from this small example itself, that it's a very complex problem to solve. So imagine that you have a multitude of user equipments being activated simultaneously. They need to access the same overlay network. The VNFs are being shared, the links are being shared, and they need to be scheduled in a different order in order for them to meet their application requirements. So how do we ensure that the end-to-end latency and the end-to-end bandwidth is met in different scenarios? And one of the possible ways of doing this is to employ modeling and analysis techniques in this 5G service orchestration problem, which is not much explored. So our solution is that we propose a UML-based modeling and analysis framework for modeling and analysis of the dynamic 5G service orchestration problem. So what we define is a UML 5G service orchestration profile, which is an extension of the existing UML models by defining stereotypes and tagged values for defining the 5G service orchestration problem as such. So if you have a case study, you can employ our 5G service orchestration framework and develop structural representation and behavioral representation using our profile, as you can see in my coming slides. So this is just an extension of our previous work where we had already proposed a UML 5G service orchestration profile, but we did not consider any dynamic aspects there. So it was just static. So here in this paper, we extended it with dynamic aspects compared to the previous work, and I will present more details in the coming slides. Before presenting the service orchestration profile, I would like to introduce you to our proposed methodology. So as I was talking, we have a 5G case study that we need to model with the help of a 5G service orchestration profile. So first step is to create a structural representation using the class diagram, which we instantiate later to form the object diagram representation, which is the runtime view of the system. And in the class diagram, we identify that there are certain classes which needs behavior to be specified. For instance, you need to invoke UE a number of times, periodically, sporadically, or you need to host, you need to have the virtual machines to schedule the VNFs and execute them. So these kind of behaviors needs to be modeled, but there are other classes which do not need their behavior to be specified explicitly as well. For example, network slice is a class does not have any behavior by its own. So there are some classes which have behaviors and there are some classes which do not have behaviors. For all the classes which we have behaviors, we call them active classes, and we try to represent their behavior using state charts, UML state charts, and we have used a pattern-based representation that can be reused. For instance, the patterns for each of the objects, active objects, we have a separate state chart pattern that is invoked to create its own state chart. And then what we do is the fourth step. So in the backend, we use model checking to analyze the system. We use UPPAAL for that. And then for that purpose, what we do is we give semantics to the state charts in terms of UPPAAL TA and create a model of timed automata that can be analyzed via model checking. So for this purpose, we have a tool called G5 that we have developed, which take in the object diagram representation of the system and invoke the state chart in the backend, which will produce a network of TA models that we can use it for model checking in the backend. So for any 5G engineer, it's only the UML profile, it's only the UML view that comes in the front end. So he just needs to input the object diagram, and the tool automatically invokes the TA profiles and creates a TA network that can be model checked. So any case study which have a set of requirements specified in natural language can be translated into TCTL formulas in the backend, and we can produce useful results to verify if our model or our system with respect to a case study model with respect to a case study can satisfy the end-to-end latency and end-to-end bandwidth requirements. So our case study, we analyzed two different applications, a health application which comprising which is actually a robotic surgery application, which uses a health slice, and a video streaming application which uses what is called a video slice. So as you can see, the health slice, we have three instances of user equipments, which are cameras that can access the health slice, which can be activated simultaneously multiple times periodically. And we have also two instances of video slice which can also be invoked periodically, and they share the same instance of the video slice. And here we assume that health slice have a higher priority than the video slice. That is always, so we employ what is called a priority based scheduling, which always ensure that the health slice VNFs are executed before the video slice instance. And
Ashalatha, just to tell you, it's half time.
Okay,
So
okay, okay, okay.
speed
Yeah,
up a
I
little
will
bit
speed up.
here.
Yeah, I'll speed up. So they need to share the same overlay network, as you can see here, with respect to 4 hosts, and then they have these VNFs allocated to these hosts, as you can see. So for this use case scenario to work, you need to find a particular routing, as I said, which goes from VNF 1 to 4 in health slice and VNF 5 to 6 in video slice, such that the end-to-end latency and bandwidth requirements need to be met in all possible scenarios. So these are some of the requirements that we verify, as I was telling: end-to-end latency, end-to-end bandwidth, and other requirements like whether all the instantiated services are eventually served in the system. So this is our profile. This is how it looks like. So we have options of modeling VNF, 5G network slice, user equipment, monitor, request handler, etc. So all the new advancements you see using the orange boxes. For instance, we have a user equipment, which is an advancement which can activate periodically with respect to an activation type. We have a request handler that is being introduced for handling the simultaneous request from user equipment, and we have a monitor which monitors the requests to see if an end-to-end deadline or end-to-end bandwidth is met. So the first step is to create a structural representation of the case study using the UML 5G service orchestration profile. And the structural representation looks just like this. So here you specify what kind of user equipment you need. For instance, you have a 5G camera for health slice and a mobile phone for a video slice. And you specify the type of slices. For instance, 5G camera uses hospital slice, mobile phone uses video slice, and you specify the category of VNFs they use, and everything is specified here. So you can also see that it is at this level we specify behavior in terms of user-defined functions. So all those classes which are highlighted with a black dot have some kind of behavior. Either it is specified by some kind of user-defined functions, or it is specified structurally, like in the case of user equipment, where you do not have any functions, but you have certain number of activations that needs to be done periodically, which is a behavioral aspect. Next, we show how the state charts are being refined. So in this paper, we use a restricted version of the UML state charts, and we call them restricted state charts because we do not use many of the parameters that a normal state chart use. For instance, we have only pseudo states of the type initial and final. There is no final state here. So if we just see the pseudo state initial, and we just have a simple state chart without any hierarchies involved, and we do not have any history states. We do not have any actions within the state. We have only actions across the transitions. So we have many restrictions compared to this, and that is why we call it as a restricted state chart. And this is how the state charts look like. So you have a state chart, one which is defined for user equipment, and one that you just saw, which shows the virtual machines which can execute the VNFs according to a scheduling algorithm. And one is for the request handler that you see, which can handle the multiple requests. And one is the monitor, which will handle the request, which will ensure that the request is being handled in a proper way, ensuring that the resource requirements are met with respect to latency and bandwidth. Now, if we have this behavioral state charts, what we do is we assign semantics to these state charts in terms of UPPAAL TA. So this is how, as you can see the formal definition of UPPAAL TA in my screen. I think I need not explain this. So for each of this restricted state chart, I have an UPPAAL TA pattern correspondingly defined. So as you can see, here is the UPPAAL TA pattern, which is used for virtual machine. And then you can see that I have model states idle and execute. I discard all the pseudo states, and I only have these active states, and I have all these actions specified in my UPPAAL model as well. So while defining the semantics, I ensure that all the things that are there in the state charts are being taken care of in my TA models, but I have also these additional constraints which like these committed locations and these clock values that are introduced. For further details, one can refer to my paper to see how exactly we are defining the semantics. So I just show an example here. Uh, and now we have this G5 tool. So this G5 tool actually takes into input both the UPPAAL TA template and the object diagram instantiation. So I haven't shown the object diagram instantiation so far because it was too big to be incorporated into the slide, but we can just see a screenshot. So we use what is called a use tool, which is a UML based specification environment to create the object diagram. And the object diagram is so this object diagram is what is being invoked in the backend, and the UPPAAL TA templates are triggered. And for each of the active objects, you have an UPPAAL TA model, which is developed by the tool. And the tool gives you actually a UPPAAL TA modeling framework that or a parallel network of UPPAAL TA models that can be model checked for a particular use case study. And so the final step is model checking and verification results. So here you can see for how our natural language requirements are mapped into corresponding TCTL queries. For instance, if the end-to-end latency requirements, we check using the leads to query, which states that if a user equipment makes a request, then it's complete, and it's modeling by construction that we ensure that the end-to-end latency and the end-to-end requirement is met. We can also check with respect to the monitor, where we verify that the monitor does not go to the fail state. If it goes to the fail state, it means that the requirements with respect to latency or bandwidth is not satisfied. And we can also verify with respect to some eventually queries that the system requirements are eventually served. Whatever requirements that get raised in the system are eventually served. And as you can see, all of them show satisfied results, although the time it took was not so much impressive, because we use exhaustive model checking in the backend that needs to verify the system exhaustively across all possible state space. Coming to the conclusions and future work, in this work, as you have seen, we have proposed a UML-based modeling and analysis problem to analyze the dynamic 5G service orchestration. So here we can a 5G engineer, a user who is a 5G engineer, can use our profile to build class diagram and object diagram representation, which enables one to represent the structure and the state charts, which can represent behavior. And we can, since these state charts are pattern based, they can be reused multiple times to represent similar behavior. And we use UPPAAL model checking in the backend. But the beauty of the approach is that a 5G engineer who's working with this tool does not need to know anything about the UPPAAL to use it for modeling and analysis or verification, because this is automated by our tool G5. But the problem that we faced with UPPAAL is that it uses exhaustive model checking in the backend. So we saw that it does not scale well due to the state space explosion problem. But there are many ways of tackling that, of course. And our future work is the work that we did very recently, was to evaluate the approach in industrial case studies by enhancing our G5 tool. So that's it all about my presentation. Thank you so much. And questions, please.
Okay, thank you so much for being on time. Just a quick question.
Yeah.
So, as I understood well, you generate the UPPAAL TA templates manually.
Yeah.
So, okay, I think that would be also very interesting interesting direction for future work. My second question is, so at the time when UML2 was standardized, there was a lot of work in pairing UML2 models with Petri nets models.
Okay. Yeah.
Can you just briefly kind of compare what are the advantages or disadvantages of UPPAAL TA to Petri nets?
So the reason why we used UPPAAL TA instead of Petrinets was that we restricted our case study into use only VNF forwarding graphs with respect to a sequence and not a graph as such. So, in that case, we can easily analyze with respect to the TA models and the state chart models to represent the system and analyze the system. But of course, if we have a more complex system and we need to analyze the graph-based representation, one can switch to Petrinets. But this just like, as I said, our approach is focusing on a framework. So one can reuse our methodology, for instance, and use until the state chart representation, and then give formalism in terms of Petrinets, and then use Petrinets for verification. So this is not a problem as per se, but the thing is that since we did not employ any kind of graph-based analysis and stuffs like that, TA model,
Right.
and since we could directly like, there are a lot of works that happened to translate state charts to UPPAAL TA models as well. We could directly do this translation, and then
Yes,
we could
yes.
accomplish what we
Yes,
need
I
with the
understood
current
it
setup.
well.
Yeah,
So
yeah,
personally, I think it would be great that you
yeah.
try to, because there were works in the past
Of course.
automatically translate, for example, UML activity diagrams to Petrinets and
Uh,
backwards from Petrinets to activity diagrams.
Yeah, so we saw
So
that, yeah, but one thing that we did not bond was that, say, for instance, if we use activity diagram for the specification of our case study, then it does not allow us to represent the behavior of individual components. So
yes,
this
yes, I
was one
understood
thing.
this.
Yeah, yeah, yeah.
Okay.